All right, welcome to a lecture about X-ray diffraction. I figured out some additional tools, so I believe that you will be able to see the laser pointer. Looks like it's there. So, X-ray diffraction, and the focus of this lecture is going to be on where the data comes from in a simplistic way, followed by some more details on what the data means and how to interpret it. So the focus of what I need you to know for this unit is how to interpret the data, not as much where the data comes from. Okay, so basics of data collection. That's the first thing that I would like you to know. I'll give you some information on how to collect X-ray data. This would be a part of the course where we would be using the new Mini in the lab a little bit. I was hoping to show you the guts of that and maybe do a couple tutorials, but obviously that's not happening. Data refinement, what does that mean? Data modeling. Understanding how X-ray data is presented, very important for me. And then what to look for in a published structure, the errors, vibrations, bond lengths, bond angles. Those are the kinds of things that you can take a look at in a published structure. So the first step in obtaining a crystal structure is to crystallize the crystals. And here we have a sample of copper ACAC. This is not this year's sample, and I don't remember who made it this year. Maybe it was you, Jenny? I don't know. But this is Emily Huang's copper ACAC from last year. And so you grow crystals from some solvent somehow. And I know I'm going to allude to this later in the week when I'm talking about a different technique. The hardest part about X-ray crystallography anymore is getting the crystals. If you've seen me using the diffractometer, you know that it's pretty straightforward. I can get a structure in about a day. So crystallization is definitely the slow step. Then you need to mount the crystal onto a holder. The holders that we use are this sort of plastic that's an amorphous plastic that doesn't diffract. There's a little circle on the end that's there's different sizes, but they're between 50 and 100 microns. So this crystal is approximately 50 microns by 2 millimeters, right? So it's a fairly small crystal, probably more like 0.2 millimeters. Anyway, it's small, and that's as large of a crystal as you need it to be. It's one of these crystals, looks like that when you zoom in on it. Then we collect the data. The data in X-ray crystallography are these spots that show up on different places on the detector. This right here is a screenshot of this data collection. This shadow right here is the shadow of the beam stop. And I'll talk about that in a little bit when I show the inside picture. But the data are these spots. It's constructive interference pattern of diffracted X-ray light, and we'll talk about that in a little bit too. Modeling and refinement is all done in the computer, and it's for a reasonable data set. Actually, solving and refining the structure is pretty straightforward. The computers are really quite good at doing this now, but there are some tricks and some things that you need to learn, and it's really a practical skill, not something I can really teach in a lecture. And then finally, present the data. So this is copper with the 2 ACAC ligands, and we can see that that's what our structure looks like. And so what I'm going to want you to understand is, what do these balls mean? What are these? Why are these different colors, different shapes? What am I looking at? So that's what I want you to get out of this. All right, so this is microscopy. This is one of the most terrifying figures I've ever seen in a textbook, and so I always use it. Here is an amoeba, but this is the giant enormo amoeba that I don't want to see. I was a biology major for a while, and this is why I'm not. So anyway, the way a microscope works is you have an object, you have an objective lens, and you have an eyepiece lens, and you can get a magnified image because the light comes into your image and it can be refracted through the lenses and can cause you to have an enlarged view. So that's what microscopy is. You can't build an X-ray microscope. X-rays cannot be focused the way that UV visible light can. And we need X-ray light because the length scale for atomic bonds is on the order of 1 angstrom, and so we need light that has wavelengths of 1 angstrom. That's X-ray light. So we can't focus the light, so we can't use this technique to get our data. So instead we use this technique. So X-rays come in from the bottom, hit our crystal. The X-rays are diffracted by constructive and destructive interference patterns. We detect those constructive patterns as spots on a detector, and then we use a computer. This looks like a laptop, but maybe not. Anyway, hopefully you're using a fancier computer than this and a crystallographer, presumably to scale with this computer. And you assemble the data into a structure which then goes into your eye. This is silly, but make sure to look directly at the structure. The phases, I will talk about this later, but the second most difficult thing about crystallography, the first being growing crystals, the second is the phase problem. Solving the phase problem is important and difficult, but modern computers can do it pretty easily for general data set. So I'll talk about the phase problem when it comes up later, but I'm bringing it up here. That's a very important input into this step of assembling the image. Okay, so X-rays are electromagnetic radiation. How do we make X-rays? How do we generate X-rays? So if we look down here, and on the next slide, I have a picture of our instrument. So we have a filament, presumably this is a vacuum chamber of some sort. This filament is under electric field. You get electrons hitting this target, and our target is molybdenum, so we're using a molybdenum radiation. And X-rays come out of these windows on the sides of the target. There's continuous radiation. So this continuous spectrum of X-rays has to do with the X-rays as they hit the nucleus or are accelerated or curved by interaction with the nucleus, or slamming into the nucleus and coming to a complete stop. That releases white X-rays, just broad spectrum X-rays that are released without sort of a focused beam. And then there are characteristic lines, the K alpha and the K beta lines. And these lines are the lines due to electronic transitions. So an X-ray, when the electron beam hits the target on an N1 electron, a core electron is ejected from the nucleus and transitions from the N equals 2 to the N equals 1 level. As that electron falls, it releases an X-ray. And it gives a very sharp band because the quantized energy gap between those shells is quantized. So it's a very narrow band. Our molybdenum radiation gives X-rays that are 14 kiloelectron volts, and it's 0.71 angstrom light. A lot of diffractometers use copper radiation, which is 1.54 angstrom light. So these wavelengths are on the order of atomic bond distances, and so we can then see at the length scale of atoms and molecules. Okay, this is our instrument. This is a big water cooling jacket for the source, which is buried inside here. Oh, I just realized I had a picture in here of our source, but it wasn't very good, so I took it out. So the source is sort of buried inside of here, and the X-rays are coming out of the source, going through this monochromator, a graphite monochromator. So in order to select for this K alpha line, we want to get rid of all this other white X-rays. And so this graphite is actually, planes of graphite. The X-rays actually diffract off the graphite at a known angle. And so the graphite is sitting here. And this is actually a curved, in our instrument, it's a curved monochromator. So it allows more of the light to enter into the beam and gives us a brighter beam. This tube here is a collimator. So any X-rays that are not going directly down that collimator are lost. And then this is the beam stop. So I mentioned the beam stop shadow. Almost all of the X-rays just hit the beam stop, and there's nothing there. There's nothing that hits the detector because we'd burn out the detector. But the small amount of X-rays that diffract off of our sample, which is just suspended right here on the end of this tip. So right here where the laser pointer is, the crystal is there, and it goes to the detector, which is, in our instrument, is a photon counter. Our instrument is a 50 milliamp, 12 kilovolt, or a 600 watt bulb, and I can't go in to look at the instrument. I don't remember it's 50 milliamps and 12 kilovolts or 50 millivolts and 12 milliamps. But whatever it is, I'm guessing it's a small number of amps now that I think about it. So 50 milliamps, 12 kilovolts, but it might be 12 milliamps, 50 kilovolts. The point is, it's 600 watts. So it's a fairly bright beam, and we're detecting the spots. So detectors have different shapes and sizes. Ours is a flat plate, and the plate is stationary. Some diffractometers have multiple ways to move, so the detector can move, the source can move, the crystal can move. And ours, the only thing that can move is the crystal. Everything else is fixed. And so you can move, you can rotate the crystal, you can move the crystal, you can get different angles of the light coming through. Here's another picture. This more clearly shows the beam stop and some diffraction data on the back there. Oh, look at that, beam stop shadow. Okay, so that's the basics of the equipment necessary. Crystals, what are crystals? Well, crystals, we all sort of know what a crystal is. It's got a characteristic polyhedral shape, looks something like this. This is actually insulin that was grown on the space station or the space shuttle, I don't remember anymore. They have flat faces, they can be ground or polished. These are crystals too. These are rocks of some sort that have fused together into multiple crystals. So we sort of know what a crystal is, but microscopically, what is a crystal? And a crystal is atoms that are arranged in a regular pattern in 3 dimensions. So it's easier to think about this in 2 dimensions, so you can tile the floor with squares or with hexagons, but not with pentagons. So in 3 dimensions, there are only so many different ways that you can fill space. The easiest way to think of is a cube. So if we look at a simple cubic structure, polonium actually has this unit cell distorted. So there's an atom at every corner, and all 3 lengths are the same. So that's a cubic structure. And we fill space 52% by putting an atom at each corner. You could put an atom in the middle. If they're all the same atom, then that actually ends up pushing these side atoms apart, so they're no longer directly touching, but they are touching along the body diagonal. We can fill 68% of space with this body-centered cubic structure. Iron, chromium, tungsten have this structure. And then face-centered cubic is another arrangement. This is actually the best that you can fill space in 3 dimensions in a simple cell. So 74% filling of space, and lead, aluminum, copper, and silver have this unit cell, face-centered cubic. We're going to move down into 2 dimensions because it's a little bit easier to see. We have a lattice, and we have the components of the crystal. So the crystal basis is defined by the type, number, and arrangement of atoms that are inside the unit cell. So in this example, the benzene molecule is the basis, and the basis repeats at every lattice point. The lattice point is a specific point in a crystal that has a specific arrangement of atoms around it, and it's repeated many times. Now, the lattice points are somewhat arbitrary, so we could have a lattice point here, or we could have put the lattice point here or here. In some cases, in some crystal systems, you have to put one of the lattice points at one point because it's a special point, like an inversion center. And if your molecule is sitting on that inversion center, then you should point the point there. But in general, the lattice points are generally movable. So if you imagine, if you have crystals filling space and you just draw an imaginary mesh around it, you can move that mesh around and still fill space. But where the position of the lattice point relative to the basis is going to be different. But there is a relationship to the point and the basis once we start solving the structure. So here are some crystals of a complex made in the Van Hoevelen lab. I believe that this is a nickel cyclam, but I don't remember, and I don't have access to the instrument, so I can't double check. But these are crystals being viewed through the microscope. They're on the order of 1/10 of a millimeter to a millimeter on a side. They're very nice crystals. Here's one that's on the goniometer head on the mount, and we're watching it in the diffraction software. So the X-ray beam hits the crystals, and due to constructive interference, we get these spots. So mathematically, we can describe these interference patterns using Fourier transforms. So F, the structure factor, is it depends on the electronic property of the atom that is being diffracted, as well as the positional property, so where that atom is and the electronics of that atom. So the intensity of those reflections is due to those two factors. So some elements, like hydrogen, are almost transparent to X-rays. They're very hard to view. Other transition elements have a lot of electron density, and they scatter the X-rays very well, and so they're much brighter to X-rays. So that's the electronic property of the atom. And then where is it? So there's an iron here and an iron here and a carbon in between them. Then you're going to see a different pattern than if it was two carbons with an iron in between it. This is Bragg's law. So we get constructive interference of these two reflected beams when n lambda is equal to 2d sine theta. So there's our theta angle. D is this spacing between these reflections. You can think of these lines as mirrors, and the X-rays are bouncing off the mirrors. That's not exactly what's going on, but the mathematics are identical. Diffraction takes place on planes that run through the crystal, and there are only so many, the next slide shows it. So here are some diffraction planes. These are the 312 planes in the unit cell of, I believe this is platinum. It's a face-centered cubic metal. And so if we look along the X, Y, and Z axes, so X, every time we go down X, within one unit cell, this lattice plane crosses 3 times, and so that's 3. Along the Y-axis, every time we move one unit cell, we get one cut of that unit cell plane. And along Z, as we go up Z, we see 2 planes. So that's why these are defined as 3, 1, 2 planes. So we index those planes by those numbers. Another way of thinking about these numbers is the vector 3, 1, 2 is the normal to this plane. So going from the origin in the vector 3, 1, 2 will hit the normal, will be the normal of these planes. And so you can have planes that are perfectly along a face. On any of the faces, you can have them at any angle. The 1, 1, 1 plane goes directly through the corners. It's the main diagonal of the whole crystal. So there's different planes, they have different orientations. And the X-rays diffract off of those planes because of the interference patterns regularly repeat along these lattice planes. Now you've seen lattice planes before, especially if you've ever driven up in the Central Valley. So this is me in the rearview mirror of my car. We're driving through wine country early in the year before they've planted. And the cool thing about this is, so look carefully at sort of like down here. You can see there's lines, or here there's some lines. I'm going to take another picture. Those lines didn't move. I'm going to go back and forth a few times so you can see it. So I'll leave the laser pointer right here and then go to the next slide. You can see that those lines are basically in the same spot. But if you look at the ground, I've driven the car. That's not the same photo, and that's most obvious back here. Look at that telephone pole moving. So I just happened to catch these lattice planes repeating as I'm driving up the Central Valley. And I made my wife stop actually on this hill and look, you've seen this before in any agricultural community or the cornfield, you see these lines. And so it's the same idea. This is a 2-dimensional lattice planes, and there they are. I've identified some of them for you. And so these are, that's what these lattice planes are. So the X-rays will diffract off these planes, and there's different orientations of those planes through the 3-dimensional lattice. And so you get constructive interference at different angles because of the construction of these different planes. So we bounce off this plane in one angle, this plane is a different angle, this plane is a different angle. So we get different diffraction peaks. Now, the constructive and destructive interference is very sensitive to the orientation of the crystal. If you move the crystal 1 degree, this is, before rotation by 1 degree, this is after rotation by 1 degree. And look at what's happening. This has gone from really only 2 spots along this arc to now having this 3rd spot grow in. And this region, the intensity of the peaks here has really changed by a 1 degree rotation of the crystal. So what we then have to do is index every single one of these points. So every single point in this diffraction image is based on a lattice vector. And we take that data, which is indexed reflection plane, and we turn that into a structure. So this is the 600 lattice plane. That's the intensity. That's the error in the intensity. So that's the data that you get out. And that's not even the raw data is just intensities and positions. And then you have to index it, and the computer indexes it pretty much automatically. So it knows that this is the 2600 plane, and that's the intensity, and that's the error. So you can have different intensities, different errors. That's the data. What we want is a structure. We want, for a protein crystallography, we want ribbon diagrams or electron density. For a real molecule, I'm showing my bias. For a small molecule, like I synthesize, we want atomic coordinates, atomic resolution, and we want to be able to have a picture that looks something like this. So protein crystal structures are much lower resolution because there's so much floppiness and there's so much data that you can't get as good of a picture as you can with small molecules where you can get atomic resolution. I'll talk more about resolution on a later slide. Okay, so how do we transform between the raw data and what we want and the process data? And this is done by Fourier transform. So there's a really good website, and I didn't check this website this year. It's usually pretty easy to find. Kevin Cowton at York University has created this little tutorial on Fourier transform. I'm going to sort of hit the highlights, at least as far as I'm concerned. So if you have one atom and you do the Fourier transform of one atom, you get a larger atom, right? So that's pretty boring. If you take a molecule and you do the Fourier transform, we have this pattern. The colors in this pattern are phase information. So the X-ray, you could be completely in phase. So the red is like, the cosine theta is 1, or it could go completely negative to cosine theta is -1. So that is the phase of the light. And when you're looking through a microscope, the phase of the light is telling you the color and the shape of the thing you're looking at. And in X-rays, that phase information would be very useful if we could get it. And I'm alluding back to the phase problem, which I alluded to earlier. We don't have phase information, and so we have to get it in a different way. If we have a lattice and you do the Fourier transform of the lattice, this is the reciprocal lattice. Notice that this line is the normal to this original lattice. This lattice is the normal to that lattice. And so there's a 1/over relationship between the lattice and the Fourier transform of the lattice. If you have a crystal at all those lattice points, we have this phase information, but sort of superimposed on this lattice. So when you do the Fourier transform of a real molecule, you get not only some information of the lattice, the regular repeat, but also the contents of that lattice. And that's shown here. So here's the lattice. Here's one molecule. If you sort of multiply these two together, you get the Fourier transform of that crystal. So the information that's here is intensity and phase, and that would give us the information we need to solve the crystal structure from the equation a couple slides ago. All right, so this is what's cool about this, is that he takes real objects or simulated real objects and does Fourier transform. So this is the Fourier transform of a duck. This is the duck. If you Fourier transform it, you get this. If you Fourier transform this, you get the duck. I don't know why his duck has lips, but it's always bothered me about these drawings, but there are some lipped ducks. If you remove the high angle data, so here we've just arbitrarily cut off the data, then we get a low resolution duck. And that's what we're seeing. What we're seeing is we can no longer see the lips, we can no longer see the wing, we don't have as much detail, we're not at as high enough resolution to see it. So in X-ray crystallography, you want bright data at high angles of diffraction to get your best picture. That's not always easy to get. High angle data can become very, very weak, but even small intensities out here will give you the resolution you need to get a good structure. And so for a small molecule chemist like myself, what we want is atomic resolution. This line spacing should be on the order of an angstrom. Otherwise, we're not going to be able to see individual atoms resolved. We're going to see them blurred together. And so the resolution distance is lambda over 2 sine theta max. And I'll talk about that resolution later when I show you some real structures at the end. But wavelength of light is 0.7 sine theta max. So it turns out if you get out to about 20 or 30 degrees of angle, that gives you a resolution of about 1 angstrom. So that's what we want. So why do we care about resolution? Well, this is a 3 angstrom crystal structure of a phenylalanine. So phenylalanine is a CH2 phenyl. You wouldn't be able to know that from this blob. Here's 2 angstrom data. You still can't tell what it is. And in the book chapter, it talks about how you sequence the protein and then you collect the X-ray data. And then if you know there's supposed to be a phenylalanine here and you can see the blob that looks like a phenyl ring, then you can assign that structure. But this is often, protein structures just don't diffract strongly because there's a huge water content in the crystals. And so you often will get greater than angstrom resolution. And so you have to do the gene sequencing or look at a lot of different techniques synergistically. And so this week we're talking about EPR, X-ray, and other techniques that I've forgotten, Mossbauer and X-ray absorption spectroscopy. And you can apply all those different techniques together to get you an interesting structure. So this is the 1.2 angstrom resolution. You can totally see a phenyl ring. There's the CH2 phenyl. So that's a phenylalanine side chain, and we know what it is. So we can see separate peaks. The crystals that I collect data on in the lab tend to have this kind of resolution. The crystals that protein crystallographers, the data that they get tends to look more like this. And that's just the nature of protein crystallography. Okay, so I'm not going to talk too much about this, but the structure factor is what we want, is what we get. The electron density is what we want. These two are related by inverse Fourier transformations. We need the phase. So we need to figure out, e to the 2 pi I is the sums of sines and cosines. And I forget what mathematical rule that is, but when you take e to the 2 pi I, that's a sum of sine and cosine. So we need to know what angle those two sine waves and cosine waves are being added together in order to figure this out and have it be non-imaginary. And unfortunately, because of the way the data is collected, we can't get the phase. This is the phase problem. We can only get the intensity. So, okay, nature could have been cool. Nature could have said, okay, if you have the intensities, that's going to give you what you need. So we're going to take the amplitudes of our lipped duck, and we're going to take the phases of a cat, and we're going to multiply those two together. And let's see what happens. So that's amplitude. So where the spots are is from the duck. The color of the spots is from the cat. And if we do a Fourier transform on this, are we going to get a duck or a cat? Well, I've hinted that the phase problem is the biggest problem, not the intensity problem. So unfortunately, the phase information carries through and we see a cat. Now, it's not a perfect cat. We have some noise. But if you were to take whatever phases you give your data is going to be what you get out. And there, it seems like then we're going to have an intractable problem, because if I don't know what the crystal structure is, then how am I going to know what phases to apply? And so this is an iterative process. And that's illustrated really well here. What if we have the amplitudes of the cat, but we multiply it by the phases of the tailless cat, the Manx cat? So what happens if we do that? So now, these two are pretty similar in terms of their amplitudes and the phases. So what do we get? Well, we get a cat, but look, there's a ghost tail here. And so what that's saying is we didn't correctly model the tail using the Manx cat. And so what we then do is plug this tail into our model, and then we can go through and get the Fourier transform. So it's an iterative process. That's the only way I can say it is you apply, if you see so this is why transition metal X-ray crystallography is easier than just doing hydrocarbons. So if you've got an iron atom or a titanium, there's a lot of electron density there. You can totally model that the brightest atom is going to be your heavy metal. And then you put that in as your model, and then the next atom out will begin to resolve itself. And so if you have some sense of what's in there, so for me, I'm looking at, here, the next slide. I'm looking at titanium that's attached to nitrogen, oxygen, or chlorine. If I can then see the titanium and then see the chlorine and the nitrogen, the rest of the structure will often build out. Now, to be honest, modern diffractometers, like the one we have in the lab, are so good and the data is so rapidly acquired that you can often, the first time the computer solves a structure, you get basically the perfect structure, for a good data set anyway. So this is a titanium complex that was made in my lab in the early 2000s. And this is its crystal structure. So what are you looking at in a crystal structure? Well, you're looking at these blobs, and they're drawn as ellipsoids, and the lines on the ellipsoid indicate how much that this atom is vibrating in the crystal lattice. So there's a structure, there's an X, Y, and Z component to each one of these ellipsoids. And so the titanium has smaller ellipsoids because it's a heavier atom. The carbons that are way out here are vibrating. This carbon is vibrating in this position in the crystal lattice. And so the size of these ellipsoids gives you a sense of the thermal motion. If you have really large ellipsoids, it might mean that the crystal has crystallized in two slightly different orientations. So here and here, and you can then go in and model both of those orientations to get a better crystal structure. So the size and magnitude of these ellipsoids is important, but connectivity, and the lines are just drawn in by the program. We've talked a lot about what a line means in Chem 104 this year, and we normally think a line is 2 electrons in a bond, but I hope that I've dissuaded you of that sometimes it's not. Sometimes it's more complicated than that. And there are certainly additional electrons, not in this case in titanium, but if this was an iron, there are other electrons on the iron that are not showing up as bonds, like the d orbital, the d electrons. So that's the picture. How can we then evaluate the crystal structure? So here's the type of information. This is right out of my publication that had these two. So this is what is published when you publish a crystal structure. So the molecular weight of the compound. A, B, and C are the lattice parameters. So it's the size of the unit cell. So this unit cell, it's a monoclinic unit cell. The space group, which is like a point group, but it's in 3 dimensions, is P21. And the size of the box is 12 angstroms by 25 angstroms by 13 angstroms. And then beta is the only angle that's given. That means alpha and gamma are both 90 degrees. So this is a rectangle that's been rotated by one angle, by the beta angle of 111 degrees. And so that tells you the shape of the crystal structure, the volume of the unit cell. Z is how many of the molecules are within that unit cell. So there are 4 of these within the unit cell. There are 2 of these within the unit cell here. This is the temperature the data was collected at. This is the radiation that was used. This is the absorption correction for the X-rays. And these are the index ranges. What this means is, well, we went from an angle of 1 to 23 degrees, 1 to 26 degrees. And I said earlier that if you have a theta of about 23 degrees, that's giving you a d-spacing of about 0.9 angstroms. So if we're getting up to 20 to 25 degrees, we're getting sub-angstrom resolution of our data. And the HKL indices, what this is saying is we saw all of the we saw all of the angles from negative 1300 all the way up to 1300 for H, K, and L. So a lot of data. We saw 25,000 reflections. That's a lot of reflections. 11,000 of them were unique. So we saw some of the same reflections twice, like reflecting off this and then rotating the crystal here, we could still see that same reflection on a different spot on the detector. So these are unique reflections that we observed. And then these are the number of reflections that had the intensity greater than 2 sigma of the background. So anything that was more than twice background, we were counting that as a real reflection. And this R factor is probably the most important factor when I'm looking at a small molecule. This is like a best least squares line fitting R factor, right? So 0.05, a 5% structure is a very good structure. A 15% structure isn't great, but obviously it got published. And then, sorry, that's R internal, totally lying. The one that's in box, conveniently, the one that is in box is the one that is the most important one. So this is the final R indices and the ones where you're only looking at where the intensity is above 2 sigma. So 6 and 4% structure, 8, 7% structure. So very good structures. Goodness of fit should be close to 1. And then residual electron density. What this is saying is there's a hole of minus 0.17 electrons per cubic angstrom and a positive 0.2 electrons per cubic angstrom. Those are the largest sort of regions of space that our model did not correctly account for the electron density in the real molecule. So pretty good. You don't want to have a large peak here because then that means there's probably something wrong with your model. For the last example, I'm going to go back to something we did in class earlier this year. So this is Sidney's and Lindy's structure of manganese and cobalt ACAC. So manganese is a D4 complex, and we expected it to undergo a Jahn-Teller distortion because of unequal population of degenerate energy levels. Whereas cobalt, we would not expect it to undergo a Jahn-Teller distortion. And so when we collected the data for Sidney and for Lindy, we saw the cobalt, all of the cobalt-oxygen distances are essentially identical. And this is me reminding myself to tell you that this 2 here means that this number is 1.891 plus or minus 0.002. So this is the error in the last digit. And the way you determine whether two numbers are the same or not is you add 2 or 3 of the sigmas, and if they overlap, then they're the same. So 1.891 plus 0.002 puts us on top of this. So these two are indistinguishable. 1.884 plus 2 sigma is 1.888, which is 2 sigma away from this one. So the point I'm trying to make is these are basically indistinguishable bond lengths. Whereas in Lindy's structure, we have 1.9, 2.03, 2.05. So these two are indistinguishable, and these two are indistinguishable. But this one, and I did the math earlier before I recorded this video, so I double checked it. This is not within 3 sigma of the 2.03. This is not within 3 sigma of the 2.03. So the manganese oxygen 1 and oxygen 4 bond lengths, these two are short. So this is a compression along Z. We'll call this O1 manganese O4 axis or Z axis. We've compressed along Z. That's our Jahn-Teller distortion. And the rest of the bonds are basically identical. So that is crystallography in a nutshell. There's way more to it than this, but I wanted to at least give you the basic introduction to crystallography. Take-home messages. 1, diffraction is limited by crystal growth, really, anymore. We diffract the X-rays off the lattice planes, and we process that using modeling to get a final structure. And we can look at bond lengths, bond angles, and vibrational motion in the solid state. So that is what I wanted you to get out of this lecture, and I hope things are going well for you.